We've invested a lot of time so far in my Machine Learning Foundation series learning about derivatives. And finally, in this video, all of the pieces come together. Specifically, in this video, we'll use automatic differentiation to perform machine learning within a hands-on code demo, enabling us to fit a regression line to data. In the preceding video, we focused on this tensor graph representation of a regression model, of a simple line model where we have m times x plus b giving us our outcome y. So now that we have that knowledge in mind, we can go forward and learn about how we can actually use machine learning to learn the parameters m and b in a regression model like this one, or really in any. So this kind of approach scales to a model with millions or billions of parameters. But here we're going to make it as easy as possible with just these two parameters, m and b. So I'm going to define machine learning here as a 4-step process. So the first step in that process is what we call the forward pass. And in this forward pass, we take our input variables. In this case, we just have one, x, and we flow that input variable into our graph, which in this case is a regression model. And so x will be multiplied by m, and then that will produce a tensor product here that flows into this operation here where we add our second parameter b, and then that gives us something that we call y hat. So this is our estimate of what y is. So prior to doing any training on data, when we've just randomly initialized our regression model with random near zero values for the parameters m and b, this estimate of y hat is likely to be quite bad. So how bad exactly? Well, we figure that out in step 2. So in step 2, we compare y hat, our estimate of what y is, with the true y that we know from our data. And so we'll compare the estimated y hat with the true y to quantify, to calculate what we call cost. And this is also known as loss. I'm going to mostly call it cost here. And so we're going to symbolize cost with the letter C. Okay, so once we have our quantification of the difference between y hat and y, we can move forward with the next step. So the next step, the third step, will illustrate why the chain rule that we've talked about many times in this Calculus 3 subject is so important. So if you kind of break down what's happened so far, we can see that we have nested functions. So in the second step, we had some function, let's call that function g, and in the hands-on code demo that we're about to have, I'm going to use a real function and some real numbers so you can see how this all works. But so let's say we have some cost function g that takes in the estimated y hat as well as the true y value that we're trying to learn to approximate with our model. And so it compares, our cost function g compares y hat with y, those are the two inputs, and it gives us that quantification of cost, of how wrong our model is. Now, in order to get that cost, so y comes from our data, that's no problem, we already have that, but y hat, we need to calculate that. And how do we calculate it? Well, we calculate it with the forward pass, with our regression model in this case. And so our regression function, our regression model f, it has 3 inputs, x, m, and b. So the input x from our data as well as our model's parameters m and b. So the output y hat is a function of x, m, and b. X, m, and b. That gives us y hat. And then from that y hat, we can use our cost function g to take that y hat value as well as the y value that we know from our data, and that gives us our cost c. So we could draw this all as a nested function here as one single function. And you'll recall from the examples that we've already carried out together on the chain rule that the chain rule is perfect for handling this kind of situation where we have nested functions, allowing us to calculate the derivative for each of the functions that are nested together. And so we have here a relatively simplistic model. I've used the simplest machine learning model that I could here, a really simple regression model with just 2 parameters. But this kind of idea where we have nested functions scales up even to deep learning models where there might be hundreds or thousands of these nested functions in a given model. So either way, whether there's just 2 nested functions like we have here or thousands of nested functions, the chain rule either way is necessary for us in order to calculate the gradient, the slope of our cost C with respect to our model parameters. So this idea is something that we are going to be focusing on in this subject of the Machine Learning Foundation series. It's going to be an even bigger part of the next subject, Calculus 2, on partial derivatives. And part of that is because in order to actually do this properly, in order to calculate the slope of C with respect to M and B, we actually need partial derivative calculus, but we're going to glaze over that for now. So we're going to talk about it at a high level now. This will be a piece of the puzzle that we figure out all the mathematics for in the next subject. But then we're going to return to this idea still, even after that. It's going to come up again and again in this Machine Learning Foundation series, all the way through to the 8th and final subject on optimization. Yeah, it really is a central idea for us in machine learning. So we're going to use that chain rule that we've learned in this subject to calculate the gradient of cost with respect to the model parameters. So what this means, by having this slope, by knowing how C is related to our model parameters, that allows us in step 4 to adjust our parameters M and B in order to reduce our cost. And the way this works is because in step 3, when we calculated the gradient or the slope of cost with respect to our model parameters, this slope tells us whether C is positively or negatively related to M and B respectively. So let's say with M, if our cost with respect to M is positive, if the slope is positive, then we know that if we were to reduce M somewhat, then our cost would reduce as well. And same thing for B. So if cost with respect to B is, say, negatively related, if there's a negative slope, then we know that if we increase B, then that will correspond to a reduction in C. All right. So this whole 4-step process is the whole idea behind machine learning. From these very, very simple regression model with 2 parameters to deep learning models with billions of parameters, it's the same fundamental idea. And the final piece here is that we loop through these 4 steps. So if we were to only go through this 4-step process one time, well, we might reduce our cost a bit, but there might be, and typically there's going to be a lot more potential. If we randomly initialized our parameters with random values at the beginning, well, the estimate y hat in the beginning is going to be poor in all likelihood. After one round of this loop and adjusting our parameters M and B in order to reduce C according to the slope that we found in step 3, well, after doing that, after adjusting M and B, our y hat is probably now going to be a little bit closer to y. Our cost will be reduced a little, but after just one round of training, there's probably still going to be room for improvement. So we can perform this loop over and over and over, quantifying, the cost between y hat and y, finding the slope of cost with respect to our model parameters, adjusting the model parameters slightly, which should reduce our cost a little bit. And by repeating and repeating and repeating, our cost will become smaller and smaller and smaller, meaning that our y hat is getting closer and closer to the true y. And Thereby, we have found model parameters m and b that fit our data nicely. So let's jump back into our regression in PyTorch notebook where we left off in the last video to implement this 4-step process and fit a regression line to some data points. Okay, so back in our regression in PyTorch notebook, we've already made our way down to this machine learning step. And so we've already kind of input our data. We already have our data lined up. So our drug dosage, as it increases for our Alzheimer's drug, we see this reduction in forgetfulness. And we'd like to now fit a regression line to those data. We saw that with our randomly initialized slope of 0.9, as well as our randomly quote-unquote initialized y-intercept of 0.1, our first randomly initialized regression line clearly doesn't fit the data very well. But let's now use the machine learning process that I've taught you about at a high level to fit this line to the data points better. In fact, we'll fit it pretty darn well. So step 1 from the slides was that forward pass. So the forward pass is this one here where we're feeding our input x as well as our model parameters, in this case m and b, and we're allowing those to produce our output from the model. And in this case, that's going to be y hat. So we already defined our regression function earlier. That's simply m times x plus b. So that captures the graph that we have here, m times x plus b. And that gives us our estimate of what y should be, our y hat. So for each of the 8 x values, 0, 1, 2, 3, 4, 5, 6, and 7, we now have an estimate of what y should be given our initially random m and b parameters. So we know from our line here that these estimates aren't very good, but let's quantify exactly how bad they are, how poorly they fit the data. So in step 2, we compare our y hat with a true y to calculate cost c. So that's step 2. So there is a PyTorch mean squared error loss method, but we're going to define it ourselves here to see how it works. So first of all, if I said to you, let's compare y hat with y, the first thing that might jump to your mind is to simply take the difference between y hat and y. And that is not a typical approach to calculating cost. So at a minimum, we would take the difference between y hat and y and then calculate the absolute value of that difference. That way, the difference between y hat and y is always positive. So cost is always a positive number. But mean squared error loss takes this one step further, and it tends to work better in a lot of machine learning situations, because what we do is we not only do we take the difference between y hat and y, but we square it. So this has the same property of cost then always being positive. So that's the same as if we were to just take the absolute value of the difference. But on top of that, by squaring, this means that the bigger the difference between y hat and y becomes, that is associated with an exponentially larger cost. So this means that we're relatively tolerant of small differences between y hat and y. Those have a relatively low cost, but as the difference between y hat and y increases, we exponentially increase the cost associated with that. So that's what mean squared error loss is. So we calculate the error, y hat minus y, that's the E in mean squared error. Then we square the error, so that's the squared error. And then we take the mean of that squared error. So for however many instances, however many data points we have, in this case we have 8 data points. So each one of those data points can be considered yi. So we sum up across however many instances we have, n instances, which in this case is 8. And then we divide by n, And that's a simple mean, a simple average. So the mean squared error cost. And remember that cost and loss are synonyms, which is why I keep calling it cost, but it's the PyTorch mean squared error loss method. Anyway, let's implement this cost function or loss function in code ourselves so that we can really understand how it works. So we calculate the error, the difference between y hat and y. Then we square it. We sum up across however many instances we have. That gives us a variable that I'm calling sigma, the sum of all of the squared differences. And then in the final step here, before we return cost, we divide by however many instances we have. In the case of the example we're working with in this notebook, we're dividing by 8 instances. So that returns for us the mean squared error cost across our 8 observations. Nice. So given our real y hat values that we have calculated here, and so we have those captured here in a tensor, and we also have a tensor of length 8 corresponding to our real y data points that we're trying to learn. So that's all the way back at the beginning of the notebook here. We initialize that. So we're going to compare the estimated y hat values, the 8 estimated y hat values, against these 8 true y hat values that we're trying to learn to approximate with our machine learning model. So we pass both of those in, our estimated values, as well as the true values that I just had at the top of the notebook, pass both of those 8 length vectors into our mean square error function. And whoops, need to run all of the code, need to define the method. There we go, and it runs. And so we see that we have a cost of about 20. So let's see if we can go through the remaining steps, step 3 and 4 in our machine learning process, and get this cost down. So step 3 was this step here where we use automatic differentiation. We use the chain rule to calculate the gradient, the slope of cost with respect to our model parameters, M and B. So you could do it by hand if you know partial derivative calculus. And in subject 4 of the Machine Learning Foundation series, which is coming up next, we will learn the partial derivative calculus that you need to perform this differentiation by hand with the chain rule. For now, we might not have that understanding ourselves, but we can rely on the PyTorch AutoDiff method to do it automatically for us. So as we learned earlier in this segment, when we were looking at automatic differentiation with PyTorch already, we saw that we can use the backward method from our outermost tensor. In this case, that's cost. And so we're going to differentiate backwards from cost over the earlier tensors in our graph. So we're going to go from cost all the way back to y hat, and then from there, continue going backwards through our regression function, and we're going to use the chain rule, use automatic differentiation to calculate the slope of cost C with respect to M as well as to B. And so we can see those exact values. So it's already run by running this backward method. We've already done that automatic differentiation. And now we can ask to see the grad, the gradient or the slope attribute of any of our parameters in our model. In this case, the 2 parameters are M and B. And we see that there is a positive slope. So what we see here is that the derivative of C, of cost, with respect to our model parameter M, is 36. So this means that there's a positive slope between them. And so following what I was talking about here, this means that knowing that there's a positive slope, we could reduce M somewhat, we could decrease M, and that will correspond to a reduction in cost C. And as it happens, the same thing goes for B. So the slope of C with respect to B also turns out to be positive. We have a 6, which also means that there's a positive relationship between cost and the model parameter B. So if we were to reduce the parameter B somewhat, that would correspond to a reduction in cost. Now, it's worth noting here that because the slope is much larger for cost with respect to M relative to cost with respect to B, it means that a reduction in M is going to have a much bigger impact on C relative to that same reduction in B. Okay, so that's step 3. And now we can finally perform step 4. We can adjust our parameters M and B to reduce cost C. So in the 8th and final subject of this Machine Learning Foundation series on optimization, we will learn how to perform this step called gradient descent from scratch. But for now, that would be too much too fast. So we're going to save that for later. And so we're going to rely in this notebook on the PyTorch built-in optimizer from the Optim module called stochastic gradient descent. Stochastic gradient descent is a very popular method for descending a gradient. Again, we'll go into all the detail of that in the 8th and final subject. For now, we can know that at a high level, the way that it works is that you pass in a list of the model parameters that you would like to adjust. So in this case, we're going to pass in all of our model parameters, which are the slope M and the y-intercept B, M and B. So we passed in this list of parameters as our first argument. And then we have a second argument here that's called learning rate. And this corresponds to how much we adjust M and B. And so this is something, again, we call a hyperparameter that you can fine tune. And we'll talk about that in a lot of detail again in subject 8. For now, you can just trust me that this number, 0.01, is a pretty good number for this particular problem that we're solving. And I've determined that empirically by playing around with some different learning rates. Okay, so now that we've initialized our optimizer, we can actually perform a step. So we call the step method, and it doesn't output anything, but it has adjusted M and B. So now when we look at M and B, they're different values than we started off with. Remember, when we initialized these values, we initialized M as 0.9, and we initialized B as 0.1. But now, because we have calculated the slope using AutoDiff of cost with respect to those parameters M and B, and then we use stochastic gradient descent to take a step based on this gradient, based on this slope between cost and the parameters, our parameters have been adjusted. So this slope that was once 0.9, because stochastic gradient descent saw, hey, there is a positive relationship between cost and this model parameter M. So if I adjust this M value downward somewhat, and how much it's adjusted is, again, it's a function of this learning rate, but it adjusts it somewhat, and it adjusted downward from 0.9 to 0.54. And similarly, in step 4, the gradient descent algorithm recognized that there was a positive relationship between cost and B. And so similarly, B was decreased from 0.1 to 0.04. So did this work? So now we can test it. So let's replot our regression plot. And our line still doesn't fit our data points very well. But if you compare this chart with our first chart of the line versus our data points, we're actually doing much better. So our x-axis is the same here, running from 0 to 7. But in this earlier chart, the slope of our line was much steeper. So we were getting all the way up to 7 here on the y-axis. Whereas now, the slope is not nearly as steep, so we're only getting up to 4 on the y-axis. So even though the line still, after just one round of our 4-step machine learning process, we don't have a line that fits the data points amazingly, it is a step in the right direction. And so we can now repeat steps 1 and 2, the forward pass and the calculation of cost. So let's repeat those. And I'm doing them just in one line of code here, which follows the formula that I had here. And yeah, repeating these steps, calculating cost again, we see that we have a cost of 8.6, and that cost is much lower. Remember, the first time that we ran this, we had a cost of about 20. And now, after having run through our machine learning loop, our 4-step process once, we've reduced that cost down to 8.5, 8.6. So that's a big jump. It's a vast improvement in reducing our cost. So we've proven to ourselves that step by step, this 4-step process works. So now we can put those 4 steps in a loop in order to iteratively minimize cost toward 0. So an epoch is a term that we use for a round of training on all of the data points that we have available. And we have 8 data points available to us. So we're going to iterate over those 8 data points 1,000 times. So I have a for loop here that will iterate over those 1,000 epochs. And you could pick a smaller number, but you'll see that after 1,000, as you'll see in a moment, that converges upon some parameter values that are not really changing anymore. So after 1,000 epochs with all of the other aspects of this particular model, the particular parameters that we initialized with, our learning rate, this 1,000 is about the right number of epochs, of rounds of training in order to get to sensible parameter values, as you'll see. So before we go through our 4-step process in this loop, we're going to call the zero grad method on our optimizer. So this is the optimizer that we used for gradient descent. And the reason why we do that is that otherwise the gradients, the slopes will accumulate in memory, wasting memory unnecessarily. So we can zero them out, freeing up some memory, and then we do our 4 steps. So step 1 is calculating y hat using our regression model. Step 2 is calculating cost, specifically mean squared error cost, using that y hat estimate of what y should be and comparing it with the actual y values that we're trying to learn to approximate. In step 3, we use automatic differentiation to calculate the slope of cost with respect to our model parameters m and b. So we go backward all the way through the mean squared error function, through the regression function, back to these parameters and calculate slope. And then in the 4th and final step, we use gradient descent to take into consideration the slopes with respect to our model parameters that we determined with automatic differentiation in step 3, and take a small step, adjust our m and b values, step them in some small amount in the direction that we know from step 3 corresponds to a lower cost. All right, and then I just have a print statement here at the end of the loop to keep us updated on some key things that are going on, what epoch we're in, how much cost there is now, and what our slope of cost is with respect to both m and to b. So let's put this in motion. It runs pretty instantly in this Colab instance. So let's scroll up to the top here to see what was happening initially, all the way back to the first epochs. And so we can see here that, so we have that cost of, so we started off with 19 before we went into this loop. And then our next round of training after that, we got our cost down to 8.5. And the round of training after that, it's down to 4, then down to 2. Very quickly, we're getting to much, much, much lower cost values. And so there's a corresponding reduction in the slope of cost with respect to our model parameters m and b, respectively. So while initially there's this large slope between cost and especially the m parameter, over time that slope is decreased because we're adjusting m, we're adjusting b, that's reducing cost, and so the slope between cost and these parameters is going down. It's getting down towards 0. Now, interestingly, you'll see here that we start to have this negative slope here. So what this means is the kind of the lowest hanging fruit, if you will, is to first adjust the slope. And so after we've adjusted the slope in a few rounds of training, then the machine learning algorithm in these epochs here starts to notice that now that slope is in line, relatively in line, there's this negative relationship between cost and the y-intercept. And so the y-intercept needs to go up in order to decrease cost. But all in all, after 1,000 rounds of training, our cost edges more and more and more and more and more down towards 0 until by the final 100 epochs, the final 100 rounds of training, the cost isn't budging at all. So it's at 0.195, and I don't see it getting any better. So it doesn't seem like there's any more value in continuing to train this model for longer. By this point, the slope between cost and both of our parameters is very small indeed. There's just really no room left to improve. And we can confirm this to ourselves by now running our regression plot again. And with our m and b values that we get after these 1,000 rounds of training, that slope and the y-intercept correspond to values that fit our data points very nicely indeed. So if you're interested in getting those final values, you can use the item method to get a nice clean float value out of m and b. And so you can see the slope here is negative 0.47, and our y-intercept is 1.75. Now note that our model, although it fits the data points very well, it doesn't perfectly approximate the slope and the y-intercept that we initialized our y values with. So right at the top of the notebook, I showed you this line function that I used to create these initial y values. And so I used a slope of negative 0.5 and a y-intercept of 2. So you might think that our model could do better, that it should be able to get negative 0.5 right on the money. It should be able to get 2 right on the money here. And the reason why our model might not ever be able to get there is because our sample of 8 data points is imperfect. So we added random noise during the simulation step. So in that step at the top of the notebook that I just showed you, we added noise, which gave some jitter to our data points around this line. And so given that, our model has really fit as well as it could, given that random noise. In the real world, the best solution would be to sample additional data points. So not just 8, but 16 or 80 or 800 or whatever you can do. The more data that you sample, the more accurate your estimates of the true underlying phenomenon parameters will be. All right, and now some exercises to test your comprehension of all of the automatic differentiation related content that we covered in this segment. So the first exercise is to try using PyTorch or TensorFlow if you like, or maybe even both, to find the slope of this function, y equals x squared plus 2x plus 2, where x equals 2. So we already solved this. We already found the slope for this function where x is equal to 2. We did that in our Calculus 1 notebook earlier, not using PyTorch, not using AutoDiff, but using the delta method. And so you can go back and look at the answer that you got using the delta method in that Calculus 1 notebook and confirm that if you use PyTorch yourself, if you use automatic differentiation, or if you use TensorFlow automatic differentiation, that you get that same slope as we did with the delta method. All right, the second exercise is to use the regression in PyTorch notebook to simulate a new linear relationship between y and x, and then fit the parameters m and b. So what this means is you can go back to this regression in PyTorch notebook. You can play around with simulating y values. So, use your own slope, use your own y-intercept. You could even play around with how much noise you have, how much randomly distributed noise. And so then when you do that, when you play around with these model parameters, then you can comment out this line of code, which will prevent overwriting y with these fixed ones. So yeah, you can create your own y values, have some fun with that. And then you can play around with other things in here too. You can play around with the initialized slope parameters, so m and b. You could adjust these. You could actually truly use some kind of random number generator to really sample random values near zero for those initial parameters in the machine learning model, and then see how things go. Just experiment with playing around with the notebook and the 4-step process of machine learning, becoming more familiar with it. All right, and then the final one is this is a fun, open-ended one for you to try. So read about something called differential programming. So use your favorite search engine to look up this term. It's a really cool concept. It could be the future of programming, could be a really big deal, where we can not only differentiate equations, but where whole computer programs can be differentiated. And it could be something that is pretty common soon, perhaps even thanks to quantum machine learning. So to get a taste of differentiable programming with quantum machine learning, check out pennylane.ai. All right, so that's all the content for this Calculus 1 subject. The next subject is Calculus 2, and in that we'll build on all of the single variable full derivative calculus that we learned in this subject, and we'll extend that to partial derivatives where we have multiple inputs, and this will be critical. This is required for the automatic differentiation that we have been applying in the last couple of videos, but not understanding the mathematics. So this partial derivative calculus is a big part of Calculus 2, and we will learn how to calculate by hand the same kind of derivatives that we were calculating with AutoDiff in this video. And so, yeah, these partial derivatives are absolutely critical in machine learning, from simple regressions like the line we fit in this video, all the way through to the most sophisticated deep learning neural networks. And also in Calculus 2, we'll talk about integrals. This allows us to perform kind of the opposite of differentiation. We can calculate the area under a curve. And this is useful, for example, for calculating a really useful metric in machine learning called the receiver operating characteristic metric. So in order to do that, we need to calculate the area under that curve, the AUC. Nice, you did it. Another subject in the books. Calculus 1 on limits and derivatives is done. See you in the Calculus 2 subject on partial derivatives and integrals in a jiffy. The segment of videos that we just finished was on automatic differentiation. We covered AutoDiff with PyTorch, as well as in TensorFlow, and we used automatic differentiation to allow a machine learning problem to be solved. In the process of that, we did also touch on cost, or what are also known as loss functions. That automatic differentiation segment was the final segment of 3 in our Calculus 1 subject on limits and derivatives. My comprehensive Machine Learning Foundation series of videos consists of 8 subjects, and the Calculus 1 subject on limits and derivatives that we're wrapping up right now is the 3rd of 8 in the series. Up next is Calculus 2 on partial derivatives and integrals. It builds heavily, very heavily indeed, on this Calculus 1 subject. Later on, we'll have other subjects forthcoming on probability and information theory, intro to stats, algorithms and data structures, and optimization. And I've colored all of these in purple because the Calculus 1 subject that we just finished proves important in all of these later subjects, but it's especially important, obviously, in the Calculus 2 subject, as well as the final optimization subject, which ties all of the preceding subjects together neatly. To be sure not to miss the next video in this series, subscribe to my channel. Thanks for taking part in this tutorial. I hope you enjoyed it. If you did, please like and comment. To be sure not to miss any of my content, head to jonkrohn.com and sign up for my email newsletter. You're also welcome to add me on LinkedIn. Simply mention that you're a viewer of the Machine Learning Foundation series. And finally, you can follow me on Twitter too if that's your social medium of choice.